Okay.
Got it?
Yep.
Okay. So, a couple of things. You all are going to be part of a very, very small experiment. Okay? So, as part of my master's, which they finally convinced me to get, I want to do a little research project on the impact of AI. Which y'all are going, what does this review have to do with AI? So this is where you all are guinea pigs. That's why I'm recording this specific one. So I'm going to upload this onto YouTube, and then I'm going to have AI generate a summary of the lecture. So to take what I'm saying and everything we talk about it, and it's going to generate a summary. And then I'm going to email that all out to you so that you have that text summary of this. So you can access the YouTube video, and then you can access the text summary of this, okay? And so basically what I want to do is get a feel for, hey, did that summary, by having AI summarize this review, did that help you? Or are you dependent upon it? Is that, oh, don't fall, okay? Well, okay, it's on film too, great. That'll live in. So, that's kind of be the small experiment, because you guys, I have never, I mean, obviously I've recorded my lectures, but I've never had AI like do a summary of it. So that's what I'm going to try and do, and so that's how you guys are the kind of the guinea pigs on this. Okay, so let's talk about this problem. So let's even just start at the beginning. So on that time up, and this is the level of work that I'm going to expect to see on the test. You're going to have an entire page to work this problem. I want to see this. I want to see the solved equation, and here's what's important. I also want to see that 0 minus and then divided by negative 9.8 meters per second squared. I'm going to look for that level of detail. Did you see physics as a tapestry? Do you understand how all of this fits together? So, I got the solved equation, I divided by 9.8, I got 1.22. Does it make sense that your time up is more than 1 second based upon an initial velocity of 12 meters per second? Why? Because your initial velocity is bigger than 9.8. Because if your initial velocity had been 9.8 meters per second, it would take exactly 1 second. My velocity was more than 9.8, so my time should have been more than 1 second. So on your velocity time graph, now this is going to be in contrast to the rocket problem. On that velocity time graph, you're going to start it at whatever velocity that you're going to throw it at. You're not going to start this one at zero like you did on the rocket problem. This one you're going to start at whatever velocity you're going to throw it at. That's when you're going to start the analysis. So what's the graph going to do? Boom, straight sloping line. If you draw this graph and you feel the urge to like curve it or make it look like a triangle, bad. Okay, bad. So, at this point, where is the ball? Maximum height. And that's going to take 1.22 seconds. Okay? Cool. What's the slope of this line going to be? Negative 9.8 meters per second squared. Nice. Great. Okay? Now, max height. This is what I would have done. And I was using the v squared minus v naught squared over 2a. There are other methods you could use to find it. I would have done it this way because you're going off of known values from the problem, okay? Now, if you wanted to get fancy, how could you use your velocity time graph to find the maximum height?
Area.
Find that area, okay? Now that you know the time, take 1.22 times 12, take half of that. But here's what you have to be careful of. That's just the distance up. That's not going to include the 8 meters because you're on top of the building, okay? So, got that. You could also use distance equals 1/2 AT squared plus V naught time. You know how long it takes to reach this maximum height. You know the initial velocity is 12. You know the acceleration. You can use that, but it's complicated, mainly because you have to deal with time squared and you got everything else. You can do it that way. That's why I said there are a myriad of ways that you can work this particular problem. Just find the one that works best for you. On the time down, Natalie, you did this one, right? Okay. So again, here's what I'm going to look for on the time down. Now, Natalie initially had a problem. She goes, man, I got 15.35 divided by negative 9.8. Problem. But here's the solution. What's your initial position on the way down?
0.
No. What's your initial position on the way down? 15.35, right? You're 15.35 meters above the ground. What's your final position going to be?
0.
How do you calculate displacement? Final minus position. Initial. So if you take 0 minus 15.35, you get a negative displacement. Now you have two negatives underneath that radical. Now the problem takes care of itself. Okay? So if you've worked this problem and you find the urge to make it, I'm just going to make G positive. No, you have defeated the whole purpose and understanding of this unit. You just can't randomly go, I'm going to make G negative, but then, that's not convenient, I'm going to switch it to being positive. And you can't, because then your velocity time graph at some point would have to have a positive slope, which is not congruent with the whole idea of having uniform acceleration throughout the flight of the ball. Okay? Now, Nathan found that the final velocity at impact. Now, here's what's important here. Again, what's your initial velocity when you start to fall? 0. It's gone to its maximum height. Stop. Fall. You've got this basic kinematic equation. V squared equals V naught squared plus 2AD. Got that equation, right? When you start to fall, the initial velocity is going to be 0. Now, this is what Nathan did that was nice. Okay? You got 2AD, and it's the same thing that Natalie ran into. I got negative 9.8 meters per second squared, because you have to be consistent. But to avoid a negative underneath the radical and irrational velocities, he used negative 15.35, which is cool. Okay? It all fits. Now you have positives underneath the radical. So the only thing about this is that you have to remember to pick the negative root. Okay? That's the only thing that, the disadvantage of this is that you have to remember to take the negative root. Now, on that time down of 1.78 seconds, here's the other way that you could have done this. This is why I said there's a variety of ways that you could have done this problem. To find the velocity at impact, what you could have done is that you could have used V equals V naught plus AT. When it starts to fall, what's the initial velocity? 0. You know your acceleration, you know it's going to fall for 1.78 seconds. The advantage of this method is that it automatically generates a negative velocity because you're taking negative 9.8 meters per second squared and multiplying that by time. So this mathematically is a little cleaner. It's fine. Or you can use V squared equals V naught squared plus 280. Okay? Those are kind of your options on that one. Okay? Then your total time is just that 2.99 seconds. That's when it's going to hit. That would be your 2.99 seconds. It's like a running clock. Okay? Cool with that. So, here are the two big problems that I promised you were going to be on the test. That rocket problem and this ball off the building problem. Rocket problem is going to be the second to the last problem. The ball off the building problem is going to be the last problem. Now, let's talk big picture. Okay? First off, this is going to be acceleration. So what equation are you not going to use? throughout this test? What's the one equation you are forbidden to use?
Distance equals velocity times.
Distance equals velocity times time. If you find yourself using that equation on this test, stop. Don't. Every acceleration problem is going to be one of two things. What's the only thing I can do on every acceleration problem?
Speed up or slow.
Make it speed up or make it slow down. If you're slowing down, what do you know about velocity and acceleration?
One's gonna go one way, the other one's gonna go the other way.
Yeah, they're going to have opposite signs. If you have positive velocity, you have to have negative acceleration. Okay, no exceptions to that rule. None. 0, zip. True or false? If an object is going to change direction, the slope of the velocity time graph must change sign. Okay, so I'm going to say this again. True or false? If an object is going to change direction, the slope of the velocity time graph must change sign.
Yes. True.
True or false?
True.
Mara, you shake your head no. Why?
Because the line can be straight sloping and still change direction.
Boom, straight sloping line. Does that slope change sign? It has negative acceleration the entire way. Does it change direction?
Yep.
How do you know?
Crosses that.
Crosses through 0 meters per second. True or false? If the slope of a velocity time graph changes sign, the object changes direction. I think that's true.
True.
So I'm going to say this again. If the slope of a velocity time graph changes sign, the object changes direction. True or false?
False.
Ella, you shake your head no. Why?
Well, you can change the sign of the slope without changing direction.
So here's a velocity time graph. It does this. Did the slope of the velocity time graph change sign?
Yes.
Did it change direction?
No.
No. How do you know it didn't change direction?
It never crossed zero.
Never crossed through
0
0
meters.
meters per second. Okay? True or false? If the slope of a position time graph changes sign, you change direction.
True.
That's true. Okay? Because if it's a position time graph, because what does the slope of a position time graph give you? Velocity. So if the slope changes sign, the velocity changes sign, which means you change direction. So basic ideas like that need to be on the test. Some application problems, okay? So let's say I give you a hill and a car, okay? And I tell you that the car is rolling down the hill and it's speeding up. And I ask you to draw velocity vectors. What would the velocity vectors look like and how would they change?
Same direction as the acceleration vector.
So would they be pointing down the hill?
Yeah.
Okay, V1, and then if it's speeding up, V2 is going to get longer. Now, if I tell you that downhill is defined as a negative value, what's the sign of the velocity? Negative. It's speeding up. So how would that look on a velocity time graph? Where would it start? Here's 0 meters per second. Are you going to start with positive velocities or are you going to start with negative velocities? Negative velocities, right? And it's speeding up. So what's that line going to do? Slope up or slope down? Are you speeding up with negative acceleration?
Yes.
Is that legal?
Yes.
Absolutely. Okay? You can absolutely speed up with negative acceleration. But what caveat is there?
Must be negative velocity.
You have to have negative velocity. So this velocity time graph is the same idea as having negative velocity vectors that are getting bigger with a negative acceleration vector pointing in the same direction. Same situation. Now, At this point, I want to slow down the car. I'm gonna hit the brakes, okay? Just hit the brakes on this side here. As soon as I hit the brakes, what's gonna happen to your velocity vectors? What are they gonna start to do, hopefully? They're gonna get smaller, right? So my velocity vectors are going to start to get smaller. So what becomes the sign of my acceleration? Positive, okay? So now I'm going to have some positive acceleration. Can I change direction with positive acceleration?
Crosses the x-axis.
Did I just do that?
Yes.
I can change the direction with positive acceleration. I just showed you that I could. Once it crosses 0 meters per second, what's it going to start to do? Speed up or slow down?
Speed up.
And it's going to, so then it would also be going
The opposite.
up the hill. So we started rolling fast, we slowed down, we stopped, we sped back up. Okay? So on a problem like that, I will define for you how I want the problem to work. Okay? You might go back and look at that on that assignment that I just gave back, the problem with the mortar, where you shoot the mortar up the hill and or up in the air and it explodes at a certain time. Okay? You might look at that one. Make sure that you understand, again, if I ask you to find the slope of a position time graph, that's the magic code for what?
Instantaneous velocity.
Instantaneous velocity, which is the slope of that tangent line. So if I ask you to find the slope of the tangent line, do I actually want you to draw the line? No, I just want you to find out, hey, do you understand how fast this is? If I gave you a position time graph and asked you to find the area underneath the position time graph, Nathan, you shake your head, no.
Nonsense.
Nonsense. Garbage. Why?
There's no such unit of meters per seconds.
Well, it isn't meter, well, it's just meter seconds, right?
Not
What's measured in meter seconds?
nonsense.
Nothing.
Nothing. This area underneath the position time graph has no meaning. If it was a velocity time graph,
Displacement.
bueno, okay, then it would have meaning. And the area would represent
Displacement.
displacement. Okay. Be able to work problems like, let's say, on that assignment that we just talked about. If I gave you the idea that I shoot something up in the air and the total time was 4 seconds. And I asked you to find the velocity when it lands. Would you use all 4 seconds? Or would you use 2 seconds? 2 seconds, why? Now, what's the relationship between the initial velocity on the way up and the final velocity when it lands, assuming that it returns back to its same height?
It's the same
Same numeric value,
with different signs.
opposite signs. Because you have V equals V naught plus AT. So if you want to look at this on the way down, what's your initial velocity?
0.
0. Acceleration is going to be?
Negative.
And you're going to use the total time or half the time? Half the time, because that's what you're going to find. In that situation, you would end up with a negative velocity, which is why on the position time graph, on the way up, initially it's going to have a positive slope. On the way down, it's going to have a negative slope. Okay? Same numeric value, opposite signs if it's symmetrical. And that's a huge if it is symmetrical. Okay, so let me hand out a couple other things.
Probably not. Yeah, I did.
Do you want this going?
On
Do you want this going?
Yeah, keep going.
same one.
That way,
That's what we got wrong. We calculated max. Number 13 on this paper.
Number 13 is like the max is the same. Or no,
No,
not that. Same.
Yeah,
We got
math is
it.
a-
You already know.
Yeah.
I know it's not, but I got this.
Okay,
Shoot.
so, what you have here, okay, so here's the big topics for the test, okay? Position time graph, slope, all the basics, terminology. That's gonna be the multiple choice portion of the test, okay? So about half the test is gonna be multiple choice. Then, on a position time graph, here's what's important in terms of the shape of it. So, if you have a position time graph for a dropped object, here's 0 meters, and you're defining the reference point as being 0, and it's going to fall away from it, what would be the shape of that graph? Linear or quadratic? For a dropped object, a position time graph.
Just a line. Quadratic? Oh, wait, yeah, the
It's
quadratic.
linear.
Ah, quadratic, why? Distance equals 1/2 AT
Squared, which is.
plus V naught time. This is time squared. As soon as you see time squared, what can it not be in terms of the shape of the graph? Cannot be linear. So this graph is going to look something like this, right? It's a quadratic function. Now, here's what's important. If you looked at your velocity time graph, what would your velocity time graph look like?
A line.
That would be a straight sloping line. And the value of that slope would be
Negative 9.8.
-9.80 meters per second squared. Understand what this slope means. At the end of 1 second, how fast are you going? -9.8. That's what the number means. For every second that goes by, your velocity is going to increase -9.8. So this is where this comes together. If you were to come out here on your position time graph at 1 second, and you were to draw the tangent line at 1 second, what would the slope of the tangent line be?
Better be
Negative 9.8 meters per second, because that's how fast it's going at 1 second. Okay, so that would have a slope of -9.8. At the end of 2 seconds, what would be the slope of the tangent line?
Negative.
Twice as much, -19.6, right? So, your velocity changes as a linear function of time because that's acceleration times time. Your position changes as a quadratic function of time because that's 1/2 AT squared. Promise you, I'm going to ask you that. It's going to be a multiple choice question. Okay? Promise you. Now, have we ever talked about an inverse relationship in this entire unit? No. So, if I give you the choice of inverse, guess what?
Not the answer.
Don't pick it. Okay? Nothing we've done has been an inverse relationship. Okay? So if you see something with the word inverse, don't pick it. It's not it. Okay? I'm just telling you straight up, nothing has been an inverse. Big thing. Do not get completely wrapped up in the equations. Solve the equation first. You only have 4 equations to choose from. And you only have 5 variables, v, v naught, distance, acceleration, and time, okay? You don't have to worry about mass. Can't plug mass into these equations if you try. You know why I've never given you the mass of the squirrel that falls out of the tree?
Doesn't matter.
Doesn't matter. You can't plug the mass of the squirrel into the equation if you try, okay? Mass of Rocky the squirrel doesn't matter. So, the other thing that you're going to get is a set of problems, and you're also going to get the answer key to the problems. No, this is not due. I'm giving you the answer key to them, okay? So, there's a couple of problems on here that if you're pressed for time, if nothing else, you work problem number 8. This is the one where you are standing on top of a building or a bridge and you throw the ball up in the air and it comes back down and it lands. Number 8 is the same idea as the rocket problem. It's just shooting a bow up in the air, okay? The only thing difference is that it's a bow versus a rocket, okay? But mathematically and conceptually, it's the same idea. When something is in free fall and the only force acting on it is gravity, what's the acceleration? But the only time you can use that, listen to me, the only time you can use that is if the only force acting on it is gravity. If you're throwing it up, throwing it down, like when it's actually in contact with your hand, or if the rocket is being fired, or the arrow is in contact with the bowstring, can't use it. But whether it's going up, down, doesn't make any difference. If gravity is the only force acting on it, that's when you can use negative 9.8. So, you're going to get the answer key to the problems. If I were you all, I would treat this as the test. Okay? I would treat this as the test. I try and work these problems, then look at my answer key to see if you got it right. Okay? So don't look at this and go, oh yeah, I would have done that the exact way Brookhampton did. Cool. Got it, yeah. Oh man, he's on fire. 10 out of 10. Okay? No. All right, Mara, stop you on the camera. I will get this transcribed